Okay, this is a question about gibbons, and gibbons are small apes that move by brachiation, and brachiation works like this. Okay, so here's my gibbon, and it got very long arms, and it's hanging on up here, and what the gibbon is going to do is it's going to swing through a circular arc over to here. Okay, so my artistic abilities are kind of limited, but the gibbon swings through a circle like so, and that's what brachiation is. Now, when I've watched gibbons do this, they move at a pretty good clip, 3.5 meters per second. That's like a slow jog. That's a pretty good clip. And they're very athletic, and doing this, I would expect this to be a pretty significant acceleration and to involve pretty significant forces. And so we can use that as part of our assessment. But the motion looks like this, except we're going to model it like this. We're going to say we're going to treat the gibbon as a point mass that's the same as the mass of the gibbon at the end of a 0.6 meter long massless rod. Well, the massless rod is the arm, and the arm is a small percentage of the gibbon's mass, so that makes some sense. As a matter of fact, the gibbon doesn't rotate, and so treating it as a point mass works well too. So this is actually a pretty decent model of the system to say the gibbon doing its brachiation looks like this. It's just a mass swinging at the end of a string or a rod. And with that in hand, we're ready to prepare to solve the problem. Now we're going to treat this as a circular motion problem, and there are two pieces that we need to consider. First off, we need to consider the motion, and we're told at the lowest point of its swing, the gibbon is moving at 3.5 meters per second. So the gibbon is moving in a circular arc, but at the lowest point of its motion, it's moving at 3.5 meters per second. The radius of the circle is just the length of the arm. That's 0.60 meters. So we know the radius, we know the speed, and the acceleration is just equal to v squared over r for circular motion. As a matter of fact, since we know the radius and since we know the speed, let's go ahead and calculate what the acceleration is, because that's surely going to be a number that will be useful for us later. And if we do that, v is 3.5 meters per second, r is 0.6 meters, I can calculate the acceleration, and it's 20.4 meters per second squared. Now I'm keeping an extra significant digit. Even though this is a two significant figure problem, this is an intermediate step in the calculation. That's part of our preparation. But the other piece we need to do is consider the forces acting on the gibbon. At this point, at the lowest point of its motion, what are the forces acting on the gibbon? Well, there's an upward force. And the upward force comes from the arm hanging onto the tree branch. So ultimately, this force comes from the tree branch. And I'm just going to call it F because exactly what type of force it is doesn't make any difference. It's just a force from the tree branch. This is an upward force, and that's the force that points towards the center of the circle. For circular motion, the acceleration is directed towards the center of the circle. The net force is directed towards the center of the circle. We know that has to be true. And so therefore, there has to be a force towards the center of the circle. This is the force. Because the only other force is the long-range weight force. Okay, have the upward force from the branch, downward weight force. Those are the only two forces acting. Net force points upward. And so with this free body diagram at hand, I can write this relationship for the magnitudes of the forces. The net force is just equal to F minus W. And F is the force that we're looking for. Now I'm going to do one more thing by way of preparation. W is the weight force of the gibbon. That's just equal to m times g. Well, the mass of the gibbon is 9 kilograms, and so I can calculate the weight. And if I do that, I get 88.2 newtons. And the reason I want to do this early is this. We're going to get a result at the end for a force that the branch must provide to support the weight of the swinging gibbon. And I'm expecting that force to be a couple of times bigger than the gibbon's weight, because this is a pretty significantly athletic endeavor right here. This is not something that I could possibly do. And so I'm expecting this force to be rather large. And large compared to the weight of the gibbon. Now we have everything we need to solve the problem. Because I can just say this, I'm looking for this force F. I'm going to rewrite this equation this way. The force is just equal to F net plus W. Well, F net, we can use Newton's second law. And Newton's second law It's just F net is equal to m times A. So F net, I'm just going to replace it with m times A plus W, but I know what the weight force is. That's 88.2 newtons. I know the mass of the gibbon, that's 9 kilograms, and we've also calculated the acceleration. The acceleration is 20.4 meters per second squared. So I have everything I need to be able to finish my calculation. Now I'm going to do this. I'm going to calculate this number right here, the 9 kilograms times 20.4. And if I do that, I get 184 newtons. Okay, and then that's plus 88.2 newtons. Because this magnitude of the net force, okay, is double the gibbon's weight. And that makes sense because the acceleration is approximately 2 g's. So that's just a way to check myself. Now I'm going to calculate what the force is by taking these two numbers and adding them. I'm going to round it to two significant figures, and I get a force of 270 newtons. Let's assess our result. At the start of the problem, I said, I think this is a pretty athletic endeavor, and I expect the force to be a couple of times bigger than the gibbon's weight. And in fact, it is. The gibbon's weight is about 90. This force is about 270. And so, in fact, this problem matches our understanding of the way the world works.